One of the last topics here in equilibrium is solubility equilibrium. And it's nice in a couple ways. One, in that it's not really that different. So if you have equilibrium mastered, solubility equilibrium really does follow all the same rules in all the same ways for all the same reasons. Two, it tends to be a little bit simpler because there's not as many possible scenarios. Some of the things we talked about in previous videos will not become involved here because we're talking about specific types of chemicals acting in certain ways. The only bad thing here, or tricky thing, is that it kind of takes something we learned that we liked that was simple and adds a little bit more complexity to it. And that is the solubility rules. So just like when we started equilibrium to say that this was kind of correcting a white lie that we had told you about reactions, this is doing the same thing. When we say there's solubility rules that things will dissolve or won't dissolve, it's really kind of a gray area in between. Some things dissolve really, really well. Some things don't dissolve really well at all. It's good to simplify them as these will precipitate or not, which is true. But when we talk about insoluble things, it's not that they don't dissolve. It's just that they dissolve very, very little. And a better term than insoluble is slightly soluble. It's fine to call it insoluble. It's great to know that it forms a precipitate. But once we get to a small enough level, it's important to recognize that a tiny bit of it does dissolve. So when we're looking at solubility equilibrium, we're still looking at a K. Rather than being called Kc or Kp, it's called Ksp, the solubility product constant. And we'll see why it has the word product in there. But the equilibrium that's being established here is the equilibrium between a solid and the ions that it breaks into. So the solid itself is our reactant. The ions are what we think of as the products. If it is truly soluble, or if it's very soluble, then that solid totally goes away and it's all ions. We have really high concentration of those ions. The ones that we're talking about here are these slightly soluble or insoluble chemicals where we still have probably a pretty good amount still together and very few ions. So what happens in this equilibrium, whether it's soluble or insoluble, us focusing on the slightly soluble, we put the solid in. Initially, there's no ions in the solution, so they start to break off. They become hydrated by the water. The attractions between the water's dipoles and those ions become strong enough to break some of those off. And they break off a little bit at a time. The forward reaction here is the solid into the ions. Eventually, we get more and more ions in solution, as we see in the second and third picture here. And once we get enough of those there, they start bouncing around, and more of them kind of bounce back into the solid. So those separate ions can actually rebond or reform back into the solid. That's equilibrium. We have an equal rate of ions breaking free and ions reforming the solid. That's our forward and reverse reaction, and it is dynamic. We may not see a difference in how much solid is there at the bottom, but it's not necessarily the exact same atoms and ions that are dissolved or in the solid state. The way we represent this is with a K expression. So we have an equation here. Silver chloride is a very common precipitate that we could make. Silver nitrate and salt mixed to make this. It doesn't dissolve very much. It's slightly soluble. Once we have that solid in there, though, it starts to break off a tiny bit, and we can't really see that. It breaks into silver and into chloride ions, and if we wanted to write our K expression, it would be the concentration of the products over the concentration of the reactants. The reason this is called a solubility product is that for every single solubility situation, our reactant would be a solid. So always on the bottom of our fraction, the denominator is always a solid, which we would represent as 1, or doesn't get included in our equilibrium expression. So it's a product, meaning that it's the concentration of cation to its exponent times the concentration of anion to its exponent. So these all have this same look, which is one of the reasons that the math for it gets a little bit easier. We don't ever have anything on the bottom, and this is where we can't get into really any weird quadratics that we have to deal with. So here's a value or a table with a few values of KSP, you can see that they're fairly small there. We generally call something soluble when the K is greater than 1. That's where our molarities are high enough that a lot of it dissolves. So our KSPs are always going to be decimals here, meaning that we are really favoring the solid, or the concentrations of ions that we have are tiny. So here's a couple of them, but it is important to recognize we do have coefficients, so sometimes we'll have exponents. So we've got some different scenarios here, big and small Ks. If we're comparing those Ks, or when we're doing math and talking about how much can dissolve, it's really important to look both at the value of the K, but also at what ions it dissociates into in terms of the subscripts becoming coefficients. This will be a scenario, and I'll talk about it with the practice problems, where you may not need to write out the whole Rice table. Because if we can just think calcium fluoride breaks into this, there's one of these for every 2 of those, the X and the 2X becomes very simple. But we need to make sure that we don't forget the subscripts and how those do turn into coefficients, and how those coefficients do becomes exponents. So that 2 on the F2 has a lot of important things when we get to the math. It goes there and it goes there. Whether something dissolves or not and how well it can dissolve is very much like any other equilibrium. The bonds, or the strengths of the attractions, the energy. So we can think about how strong is the bond in the solid, how strong is the attraction within the water, how strong is the attraction between the water and the ion. That's one of the things that determines whether a lot will dissolve or little. Another thing is how orderly, or what we call the entropy of this. So how orderly is our solid? How orderly is our pure liquid? How orderly is our solution? And how orderly, and how, I guess, do those ions impact the order of the water? Because when we have an ion, we do know that water surrounds it, and it surrounds it in a certain way. So sometimes we can predict certain things about delta H, delta S, or those attractions and the strengths of them. But overall, there's usually lots of factors where we need to be given some calculations or given some more numbers to know those things for sure. But in general, we're just talking about solid breaking into ions, and with slightly soluble in KSP, it's doing at a relatively small amount.